Okay, this is problem 11 of section 1.5. So we see that it references graph of the function and use a graphing utility to confirm your answer. Just kind of cross that part off. If you want, we can do that. We probably will do that, but you aren't required to do that. And on an exam, you're not going to have a graphing utility. So don't worry about that portion of it. We really want to be able to do this analytically because that's what we're going to see, you know, without that software. Software is great to reinforce what we already know, but if we don't know it without the graphing software, if we're using it just as a crutch, you know, we're not going to be able to do these problems. So we want to determine if the graph of the function has a vertical asymptote or removable discontinuity when x equals -9. So removable discontinuity, one of the things is if it's discontinuous at x equals -9, and given the context, I think we can assume that it is. To determine the type of discontinuity it is, we need to kind of look at, well, why is it discontinuous? So the requirements for something being continuous is one, that f of, in this case, -9 has to exist. In this case, it doesn't exist. So that right there crosses off the potential for it being a place of continuity. We need to look at the limit as x approaches -9. And so hopefully that exists. If it doesn't, then we know we don't have removable discontinuity. Okay, so let's go ahead and explore this limit because we already know it's discontinuous because it doesn't meet that first criteria. So we look at the limit as x approaches -9. We have of x plus 9, x minus 9 over the quantity x plus 9. And we have a common theorem that we use that say if we can find an equivalent function that agree at all but one point, so that x plus 9's, you know, we can kind of cancel those out. You know, it might be good practice just to note that, hey, x does not equal -9, and it doesn't. You know, we're gonna say that the limits are equivalent, but the functions are, and that's why it's also very important to keep that limit notation on there. So we're looking at the limit as x approaches -9, because again, these aren't equivalent functions. Their limits are equivalent, but the functions aren't. So we have then of x minus 9 and then over 1. So then here, if I want to directly substitute in -9, I get -9 minus 9, which gives me a -18. So the third criteria in order for the function to be continuous is that f of 9, -9 has to equal the limit. So 1 and 2 have to both be defined, and then they have to also equal each other. So that limit as x approaches -9 of x squared minus 81 over x plus 9, we saw that that equals -18. And so if we could just go ahead and fill in that one spot, that would solve our discontinuity. So we could say then let's let f of -9 equal -18, and now it's continuous. Now all three criteria are met, and it is continuous, so we have that removable discontinuity. Something that would be telling me that it's maybe a vertical asymptote is if that limit in problem 2, if we were working it out and that limit was approaching infinity or -infinity, or maybe the limit, you know, didn't exist, but if the left and the right limits existed and they approached infinity, that would say that we have a vertical asymptote. That didn't happen here, so we can be reassured that, you know, analytically we don't have that vertical asymptote. Now I am going to reference graphing software. Again, not required. We did that problem completely analytically. This is just kind of to reinforce, and that can be nice to do, but it's not essential. Definitely, you know, the answer key is nice, but you should be able to do the problem without the answer key. That's what this is. This is just that reinforcement. I've already forgotten the function. Okay, so I'm going to desmos.com. And we want to look at f of x equals x squared, squared minus 81. And I'm going to put parentheses and then over x minus 9. Let me check that again. X plus 9. Okay. So we checked our graphing software. We graphed it. Now you might be looking at this and say, well, what? It looks defined. If I go to where x equals 0, it looks defined. But actually, if we're actually looking at -9. But if I go to where it equals -9, and I might have to zoom out even a little bit more. And then go to -9, and you could check this with the table. Very touchy. It does come up undefined. It has that open circle. Very hard to see graphically. And like I said, unless you really touch that point where x is -9, you don't see that. But we see that it does just have a hole. It doesn't have a vertical asymptote there. So that does reinforce what we've already found. And our graph would look a little bit different, right? So